Hi everyone, my name is Scott Michael. I'm from Indiana University. I'm going to talk to you today about some performance benchmarking that we've done on the Knights Landing architecture for the R interpreter. Just a brief note about who I am. I'm actually not a statistician, so I'm a theoretical astrophysicist who does HPC application optimization and happens to manage a team of research analysts at Indiana University. So this is going to be mostly focused on HPC architecture and benchmarking, not many stats, but there'll be some plots. I'd like to thank everyone who has contributed to this project. We have a team both at Indiana and at the Texas Advanced Computing Center, and there's been a lot of work done on this project. So just to give an overview of where I'll be going today, I'm going to talk a little bit about the motivation behind doing this benchmarking of this particular architecture for R, give some results from the benchmarking that we've done, introduce a package that we've created called our HPC benchmark, and then talk a little bit about what we're going to do in the future. So, how many people here are intimately familiar with the Xeon Phi computer architecture? Yes, okay, so I can say anything now. That's good, because I have lots of slides that are going to tell you all about the technology. But the reason that we're interested in this is that we have a partnership at IU with the Texas Advanced Supercomputing Center, who provide a supercomputer called Stampede, which one of the main components of this supercomputer is the Xeon Phi accelerator architecture. And our part of the collaboration is to provide support to users who want to use sort of high productivity languages like Python, R, MATLAB, etc. And so we had done this provided support for these types of languages on the first instantiation of Stampede, which is called Stampede 1, and we were moving to a new machine called Stampede 2. There is a big transition because there was a change in architecture between Stampede 1 and Stampede 2. So Stampede 1 is a more traditional supercomputer that's based on the Knight's Corner accelerator, so the Xeon Phi called Knight's Corner, and Stampede 2 is based on the Knight's Landing architecture. The main difference, the main takeaway, other than the fact that Knight's Landing purports to be much faster than Knight's Corner, is that Knight's Corner is coprocessor only, so it acts as an offload accelerator, and Knight's Landing can be either a coprocessor or a self-hosted chip. So basically, you are not required to shuttle your data back and forth to the processor. The entire operating system and everything runs on the Knight's Landing system. And so these are the sort of base specs for these two architectures that come from sort of marketing material. No one ever sees this kind of performance out of these things, as we'll detail in a minute. So when the support that we had done on Stampede 1 was basically supporting specific use cases, distributed and parallel versions of R. We had built R in offload mode to run on the Knight's Corner accelerators, and also Stampede 1 had a few GPUs, which we had run some GPU-based code via R on Stampede 1. However, most of the workload that was based on R on Stampede 1 simply used the underlying CPUs, which are Sandy Bridge. It's a dual socket server. It's very sort of plain Jane and not super interesting. So there were 6,400 nodes of dual socket Sandy Bridge in Stampede 1. In Stampede 2, there are about a little over 4,000 nodes of Knight's Landing. So the only processor you have to use is Knight's Landing. And the question is, how will R code or Python code fare under this new architecture? And the reason that you might expect there to be some difference is that the Knight's Landing architecture is quite different from sort of a standard CPU, a Xeon server type processor that you would see. So people have done a lot of benchmarking and improving of the technology on sort of standard Fortran and C-based HPC type codes, a lot of molecular dynamics, climate, astrophysical codes. But the question was, how would something like R do? So this is the basic architecture of the Knight's Landing. So it's a 2D mesh of anywhere from 64 to 72 cores. The parts that we were testing had 68 cores each. The cores are divided into tiles, each having 2 cores per tile and a shared L2 cache. And this is sort of the vector pipeline that the hardware implements. Each core can support or supports 4-way hyperthreading. So on the parts that we were looking at, you got up to 272 hyperthreads. There's also each chip has 16 gigabytes on board high bandwidth memory called MCDRAM, which can be configured in a variety of different ways. And we tested, you can treat it as sort of separate addressable memory or as a L3 cache, basically. So we tested both of these, and in the end, we didn't see a lot of a difference in performance between these two options. So our strategy was to get a set of sort of industry standard micro benchmarks and run them on the Knight's Landing architecture, run them on Sandy Bridge, and compare to see what users might expect to see in terms of performance when they moved from Stampede 1 to Stampede 2. So that's step one, and that's basically what I'm going to talk about mostly today. Then what we're hoping to do in the future is look more in depth at some exemplar workflows that people want to use on this system, and see how those compare between the KNL and the Xeon or the regular Xeon server line. We'd also like to do both single and multi-node benchmarks. Today, I'm only presenting single node benchmarks, but multi-node is in the works. So as you search around looking for sort of standard benchmarks, this R25 benchmark keeps coming up for a suite of micro benchmarks. I was very happy to hear that there's a new set of benchmarks. We found that this was a little hard to work with because it didn't easily allow for changes in matrix size, thread count. It didn't allow us to sort of automate the testing. So basically we wanted to test for all available thread counts and a variety of different matrix sizes for all of the dense matrix operations, some sparse matrix operations, and other packages as needed. So we built a package called RHPC Benchmark, which allows you to do just that. It currently contains a set of benchmarks that are sort of micro benchmarks, but we're happy to have people add to that framework as well. Okay, so what did we see when we ran on this system? The real power of the architecture is that there are many sort of not super powerful cores. Each one of these cores only operates at 1.6 gigahertz. And so compared to a standard core, even in your laptop is not very powerful. But if you have a code that can be threaded or easily parallelized, then you can potentially get a lot of benefit. We sort of took the easy way out in that since we're doing a lot of dense matrix operation, we rely on the threading in the Intel Math kernel library to do much of our optimization. Wanting to look at sort of what is the overhead and sort of that the R interpreter introduces for this sort of these types of operations. So the first thing we found was that the hybrid threading, and this has been seen widely in many of the different application areas, the hybrid threading doesn't really get you a lot of performance benefits. So this transition here is at 68 threads, which is the number of physical cores on the system. And so these are a couple of examples for some of the scaling benchmarks that we ran. There's a list of all the benchmarks that are included in the package up there. And so running multiple threads per core is not useful in improving your throughput, which was a contrast to the Knight's Corner accelerator architecture, and that was for very specific reasons in the architecture, which I can be happy to talk about offline. Another surprising result was that for some benchmarks, we found that actually single core performance on Knight's Landing was better than the Sandy Bridge. So, sorry, I should just go back. In all of these slides, we're looking at execution, either execution time or scale performance versus thread count, and the Knight's Landing is in red and the Sandy Bridge is in blue there. And so when we look at the runtime here, we see that Knight's Landing is actually faster even at a single thread. And this is, we suspect, due to AVX 512 implementation in Knight's Landing, which is not available in Sandy Bridge. In order to really make use of the scalability of the Knight's Landing system, you need fairly large matrices. So we did a variety of different matrix sizes ranging from 1K squared to 20K, and you see that for a 4K by 4K matrix, the Knight's Landing is always slower than Sandy Bridge, but for a larger matrix, a 20K matrix, it outperforms after 4 or 8 threads. And then to just sort of measure the raw overhead of the R interpreter, we implemented the MKL calls as a C driver and just ran both of these and timed them, so the R wrapper versus the C driver. There are actually 2 lines there, they're just kind of stacked on top of each other. So the R interpreter overhead for this particular application, these particular micro benchmarks, is fairly low. So as I said, we have a package which is very flexible and allows you to configure how you want to run the benchmark and produces nice machine readable output that you can then graph and share. So in the future, we're going to measure internode performance. As I mentioned earlier, we want to look at some more complex functions and workflows and different types of functions. We have some sparse matrix benchmarks in there now. We'd like to add a few more, look at some more machine learning benchmarks and things like different types of data wrangling. So the takeaways, you can actually get better performance on this hardware, a single socket KNL, than a dual socket server of Sandy Bridge. So at best we saw 3 times better, and that probably holds true even for more current releases of the Xeon server line. The performance that we saw is best for very large matrices, and we have this CRAN package that we'd like you to go check out and run benchmarks. And that's all I have, so I'm happy to take questions.
Yeah, thank you. So this is actually exactly the opposite to the former talk, right? So you're now actually benchmarking the BLAS rather than R, because you have micro benchmarks and matrices of operations that are actually in a standard BLAS already, and now you have a BLAS for the graphics hardware and do some benchmarks for it.
Yeah, I mean, that's a fair assessment. I think that we were interested in looking at, what's the overhead, if any, how are things handled for our passing off to the BLAS. And so basically, we did see that there is fairly good optimization for the Intel implementation of the BLAS algorithms.
So what did you do about the checks for non-finite values? In R, until very recently, the matrix, or by default still, the matrix products will check for NaN values and inf values in the inputs. And this check is run on one core. And in some benchmarks, this can actually be a big part, right? So what did you do about this?
Yeah. I don't think we ran into that as being an issue, and I would have to look at the implementation again, but I think it's probably due to how we're generating the matrices. I know that something along those lines did come up, but I'd have to follow up with you after.
Yeah. Of course, this is bad for scalability, right? If this check runs on one core and takes half of the time, for instance, and only the rest is in BLAS.
Yeah, and so that's mostly what we were concerned with here, measuring, sort of intercomparing the architectures and looking at the scalability on this particular hardware.
Yeah. In current R, you can disable the checks for this type of benchmark. So, yeah.
So if you have a box with Knight's Landing, and what do you need to do anything special to use R? Do you need to build it specially, or can you just run?
Well, so it's pretty straightforward. You can just build R. So this is built from source and linked against the Intel libraries. There's not a lot of special things that you need to do. You do need to configure your environment to make use of the MKL libraries appropriately, but that's sort of described how to do that in the package.
And sorry, just one more question. How do all of these cores appear to software? Like if you query the number of cores, do you see 68 or 72? Or?
Yeah. So if you can run with or without hyperthreading. If you run without hyperthreading, it's just however many cores they appear as regular cores. And with hyperthreading, the OS sees 272 cores. So all of these runs were done with hyperthreading turned on, and so the thread placement's actually pretty good because we saw fairly good scalability all the way up through 68 cores. There's also the thing that's a little trickier is the memory configuration. So whether or not the high bandwidth memory appears as a separate NUMA node, there's actually several different configurations for that memory that you can